Good morning. I'm going to have a look in this video here. We're going to do pages 409 to 411. So we'll just write that in there. Pages 409 to 411. And it's more or less to do with radioactive decay. So that's where our starting point will be today. Radioactive decay. And radioactive decay is one of these things that's probably misunderstood for many different reasons. But the thing about radioactive decay is why a nucleus changes is that the nucleus is unstable. And it's unstable because the proton to neutron ratio, protons divided by neutrons, should equal 1. Now if you go back to the likes of uranium 92, what am I, I'm not in the zone here, hang on, undo. Right, 1. So if we take uranium 92 235, well, this tells me it's got 92 protons. I'll do my wee PEN again. So it's 92 protons, so therefore if it's a neutral atom it's 92 electrons. But how many neutrons has it got? Well, the neutrons, that number there is protons and neutrons, and that number there is the protons. So it's 235, take away 92, gives me 143. So the proton to neutron ratio is not 1. See that? 92 divided by 143 is not 1. So there, that's why uranium is unstable. And the number is 1 because God has chosen it to be 1. Fair enough. So that's why they're unstable. Proton to neutron ratio should be 1 to be stable. And if it's not 1, it's unstable. Fair enough. People who are famous that looked at this sort of thing were Henri Becquerel. Henri, he wasn't from Newry anyway. He'd be called Henry if he's from Newry. Henri Becquerel, he investigated it as well. The thing about radioactive decay are the changing of a nucleus, the splitting of a nucleus, is that it's spontaneous. That means it could happen at any time, right? And it's a random event. So again, spontaneous and random, similar. And there's no external influences. So in other words, things like heat and pressure and light and things like that, they have no real influence on it at all. So you could never say when it's going to split up. And we had some famous scientists like Curies, and they were married. The Curies were married. It was Pierre and Marie Curie. And here comes the stupid question for the day. These people investigated radioactive decay, and people would say they probably died of radiation sickness or radiation poisoning or cancer, but they didn't. Marie Curie did, but Pierre Curie did not. He was knocked down by a horse. So they lived in Paris in the early 1800s, early 1900s, and he was killed by a horse. Marie Curie, the Marie Curie nurses that we now know, like around when people have cancer, but she did die of cancer. So that's why the Marie Curie nurses are what they are. So this radioactive decay, the nucleus becomes more stable, or tries to become more. Nucleus tries to become more stable, and by doing so, more stable, and in doing so, it fires out particles, and the 3 particles that it fires out are called alpha, beta, and gamma. Now these are the 3 letters of the Greek alphabet, like A, B, and C. Now these are the 3 radiations that you have to know. So let's just take the first alpha. Now alpha is like a helium nucleus. If it was a helium nucleus, it would come from helium. What you would do is take a helium atom, you strip the electrons of it, and you get a helium nucleus. But alpha particle is like a helium nucleus. It is not a helium nucleus. It's like a helium nucleus. And the helium nucleus, if we go back to, remember in the last video we did A cross zebra, right? Well, it's 4,2 He is your helium nucleus. So when this alpha particle is fired out, it's got 2 protons, so there's it there, look, 2 protons. It fires out 2 protons, 2 neutrons to become more stable. That's what it does. So it changes the proton to neutron ratio. It changes that ratio because it fires out 2 protons and 2 neutrons, and it becomes more stable. It still may be radioactive. So that's your alpha particle. Now your beta particle, and here is sort of the strange in this. It's a fast moving electron from the nucleus. So fast moving electron, but you would say to me, oh, all the electrons live on the shells orbiting the nucleus. And I say you're right. But what they believe happens is there's a neutron. There's the symbol for a neutron, and it splits into a proton and an electron. And it's this electron that is fired out. And the proton stays in the nucleus. That's what they believe happens. Right? So, neutron splits into a proton, an electron. The electron is fired out, and the proton stays in the nucleus. That is beta decay. So it's like a fast moving electron, not E minus 1. Well, it actually is a fast moving electron. That's the symbol for it. Now, gamma rays are just pure electromagnetic waves. An electromagnetic wave is all the waves in the electromagnetic spectrum, which is radio waves, microwaves, infrared, light, ultraviolet, X-rays, and gamma rays. And it's the last one, this is what, and it usually is associated with these other two. It doesn't usually exist on its own. Usually when these things change here, right, this occurs. So when these happen, usually this happens. Fair enough? Now, so let's look at the properties of these. Now, alpha particles are the most dangerous to humans if ingested. In other words, don't eat them. And you would say you didn't want to eat them, but if they're on food and you didn't know it, you still eat them. If ingested or inhaled, so don't eat it or sniff it. And the best way not to eat it or sniff it is not to be near it. So don't eat it, don't sniff it. It's stopped by paper. So it will, your skin will stop it. It may burn your skin, but your skin will stop it. But if you eat it, it'll get inside and it'll damage the cells. And the reason it damages the cells is a good ionizer. That's the reason. It's a big, slow, cumbersome sort of thing compared to the other two ways. And for that reason, it can interact with cells well and changes the structure of the DNA, and therefore once the structure of the DNA changes, the cell doesn't do what it's supposed to do, and that becomes a cancerous cell. And that's why why alpha particles are dangerous. They're dangerous because of that reason. They're good ionizers, so therefore they interact with cells well. Once you change the nucleus of a cell, you change the structure of that cell, and once you change the structure of a cell, that is a cancerous cell. So then we'll go on and we'll have a look at the beta particles, if we can get this thing to move. And we're talking about the beta particles being fast moving electrons. And these fast moving electrons, they can also interact with human beings, right? They ionize less than alpha, but they still ionize, they still can pass through your skin. It takes several centimeters of aluminium. Aluminium stops it, but it has to be, you know, several millimeters of aluminium. But your skin's not aluminium, unless you're a tin man or something. And therefore, it'll pass through your skin, and again, if it interacts with cells, it can also cause problems. So then we'll go on to the last one here. We'll go on to our dear friend, old gamma. Now, most people think that gamma is the most dangerous, and it is dangerous. There's no point in saying it's not dangerous. But of the three, it's probably the least dangerous. The alpha is the most dangerous. That's next, and it's next. Not that you want to be in the presence of any of them, but if you were to be in the presence of any of them, well, that's what you would be. And it's just pure radiation. And it does interact with cells, and it does cause problems to cells. But if you keep out of its way, it'll not do you much harm, like most things in life. So it's just pure electromagnetic wave, and it can cause cancer. But so can the other two. It's also used in radiotherapy, where it's given in controlled amounts to kill off cancerous cells. So the last thing I want to look at, I suppose, if you made up a table of them, if you want to develop your own study skills, if you made up a table of them, that might be a good idea. But here's how to reduce the risk of getting cancer from these things. Again, all you can do is reduce your risk. You can't really do away with them. So if you wanted to reduce your risks of when handling these things, which for you would be illegal because you're under 16 and shouldn't be next to near it anyway, but the answer is you wear protective clothing. Now, whatever that means. Seal suits, suits with lead linings, whatever suits you, the protective clothing. It depends what you're wearing and what you're handling, so you wear protective clothing. You use tongs as if you were putting something into the fire, because therefore it'll not be in contact with your skin, it'll not be near the surface of your skin, so that's why you're using tongs. And then the next thing would be little exposure time. So in other words, don't be in its presence unless you need to be. And then the last one is a lead-lined castle. It's not that you're a princess or something living in a castle. This was a lead-lined, wasn't a very sick princess. A lead-lined castle means that lead absorbs all of these. Absorbs alpha. Please, machine, come with me. Alpha, beta, and gamma are all absorbed by a lead castle. So therefore, if you put the radioactive source in a lead castle, you do not let the alpha, beta, and gamma radiations out. So that's why you put it in a lead castle. So that's more or less page 409 to 411 covered. You can look at the types of alpha, beta, and gamma radiation and then make up your own table and revise that. Whatever way suits you. And that's it. See you shortly.